Molecular polarity. Molecular polarity is probably the most challenging topic in this chapter. However, if you do understand the molecular geometry and the bond polarity, it will not be that challenging for you. I would like to remind you, if you are not very good at molecular geometry, you may want to go back, review that section again before you proceed with this lecture. So what is it? What is molecular polarity talking about? Remember the bond polarity? For example, a bond between hydrogen and fluorine. Do you remember that? Bond polarity describes how the electron pair or pairs are shared between two atoms. If it is shared evenly, it is called a nonpolar bond. If it is shared unevenly, it stays closer to one than the other, then it is called polar bond. So bond polarity describes the electron distribution between two atoms. Well, molecular polarity describes the electron distribution within a molecule. If the electrons are distributed within the molecule unsymmetrically, then it is a polar molecule. If the electrons are distributed within the molecule symmetrically, then that's a nonpolar molecule. Now, given a molecule, how do we predict if it is a polar or nonpolar molecule? Well, I have laid out a 3-steps procedure. Let's keep practicing these 3 steps. You will become an expert on this. So first of all, in order to know the polarity of a molecule, you need to know the molecular geometry of it. Remember the overall procedures to figure out the shape or geometry of a molecule. You need to draw the Lewis structure first, then decide the electron arrangement. It could be linear, it could be trigonal planar, it could be tetrahedral. Then you predict the molecular geometry depending how many electron groups around the center atom are bonded, how many are non-bonded. Then you predict the geometry. Again, if you don't know what I am talking about, you need to go back to go over the molecular geometry lecture before you proceed. Otherwise, you could learn barely anything from this lecture. After you know the molecular geometry, you consider the bond polarities between all the atoms that are bonded together. Then you can make a conclusion on the molecular polarity. Well, I always want to use our little creatures model to talk about the molecular polarity. Okay, remember, in a molecule, given a molecule, consider all the atoms that are bonded inside a molecule, consider them as a little creature. When they're bonded, they are playing the tug of war. Okay, consider each atom in the molecule is playing tug of war with all the other atoms that are bonded to it. So all the atoms standing there pulling hands with each other, pulling around. As a result, if the whole molecule is going to move to one direction, then it is a polar molecule. If all the pulling forces cancel each other, that's a nonpolar molecule. The molecule is not going to move. Okay, let's use some examples to go over this. Predict the polarity of hydrogen cyanide and carbon dioxide. All right, let's follow the procedure. Predict molecular geometry first. To do that, we draw the Lewis structure. I assume you know how to draw it. This will be your final Lewis structure. This will be your final Lewis structure. All right, now predict the molecular geometry. There are two groups of electrons around the center atom. As a result, this is a linear molecule. There are two groups of electrons around the center atom. As a result, this is a linear molecule. Well, now let's talk about bond polarity. Hydrogen-carbon bond. Carbon is a little bit more electron negative than hydrogen, not a lot. If there's Na polarity, it's very small, but overall, carbon is stronger. Okay, if they are playing the tug of war, carbon is going to win over hydrogen. Nitrogen is more electronegative than carbon. If they are playing the tug of war, nitrogen is going to win. As a result, the whole molecule, if they are playing the tug of war, is going to move to the right. Does that make sense to you? That's a polar molecule. What about the carbon dioxide? Carbon dioxide, oxygen is more electronegative than carbon. Oxygen is more electronegative than carbon, so oxygen is pulling carbon towards that direction. Oxygen is pulling carbon towards that direction. Two oxygens have equal electronegativity, so the two forces cancel each other. Although the carbon in the center are being pulled hardly, okay, strongly, because oxygen is very electronegative. However, overall, the molecule, because it is linear, the molecule is not going to move to any direction. So this is a nonpolar molecule. Make sense? Now I hope everyone have realized that in order to know the polarity of the molecule, you do need to know the geometry and bond polarity. Both molecules, in this case, hydrogen cyanide, carbon dioxide, both molecules have polar bonds in it. However, if you talk about the molecule as a whole, the first one is polar. The second one, carbon dioxide, even if it has polar bonds, it has two polar bonds. However, the whole molecule is nonpolar because the two forces cancel each other. From our conclusion from last slide, we can summarize that to be a polar molecule, there must be polar bonds. If within a molecule there's no polar bonds, atoms are just holding hands, not pulling at all, that's a nonpolar molecule. So to be a polar molecule, you must have polar bonds in it. However, to have polar bonds within a molecule is not enough to make a molecule polar. You have to consider the geometry as well. In the case of carbon dioxide, you do have polar bonds, but the overall molecule is nonpolar. If the molecule has a symmetrical electron distribution, it will be a nonpolar molecule regardless if there are polar bonds or not. If the electrons are distributed within the molecule symmetrically, then it will be a nonpolar molecule. Okay, let's move on. Continue to practice this molecular polarity. Again, this is the steps we're going to follow, and this is what you need to think about the atoms within a molecule. They are pulling towards each other. They are playing the tug of war. And if overall the molecule is going to move, it is a polar molecule. If the molecule is going to stay there, not moving, all the forces cancel each other, that's a nonpolar molecule. So let's look at what practice we're going to do this time. Predict the polarity of carbon dioxide. Oh, we just did carbon dioxide. And sulfur dioxide. Oh, these two molecules look so alike. But they're asking us to compare the polarities of the two. The first one, we just did it. Let me see if I put it here already. Yep, it is a nonpolar molecule. We know that. That's our conclusion. Sulfur dioxide. Let's follow this procedure. This will be the Lewis structure of sulfur dioxide. actually this. So there's a double bond between carbon, oxygen, sulfur, and a single bond between oxygen, sulfur. Well, this is the loose structure. There are 3 groups of electrons around the center atom, so electron arrangement will be trigonal planar. Out of the 3, only 2 are bonded to oxygen atoms, so the overall molecule geometry will be angular. That will be the shape of the sulfur dioxide molecule. I did not put the lone pair here. It's not a big deal in this case because we focus on the center atom. All right, now let's look at the bond polarity. We know this is the geometry angular of the molecule. Let's look at the bond polarity. Oxygen is more electronegative than sulfur, so this bond is being pulled away from sulfur towards oxygen. So if they are playing the tug of war, oxygen is winning. This oxygen is also winning over sulfur. As a result, if the 3 atoms are pulling each other like this, the whole molecule is going to move downwards. It's going to move down. Does that make sense to you? So this is a polar molecule. Sulfur dioxide is a polar molecule. What I am trying to say here is that look at carbon dioxide, sulfur dioxide. They look so much alike on the formula. However, carbon dioxide is linear, is nonpolar. Sulfur dioxide is angular, is polar. Predict polarity: water, ammonia, methane. Water, Lewis structure. This is not a molecular geometry. Ammonia. Again, these are the Lewis structure, not a molecular geometry. We need to predict the molecular geometry. Now, if you go through the molecular geometry procedure starting from the Lewis structure, which I put here, you will finally get the conclusion about the geometry like this. Methane will look like that. Well, the center one here is a carbon. It's going to be a tetrahedron geometry. Ammonia is going to be trigonal, pyramidal, nitrogen on the top, 3 hydrogens lower. Water will be angular. Now let's move back to the last one, methane. If the whole molecule is taking this shape, regardless if these bonds are polar or not, you know this is a tetrahedron geometry with 4 hydrogen atoms at the vertices of the tetrahedral shape. Overall, electrons are distributed symmetrically. If they are playing the tug of war, the molecule is not going to move to any direction. So nonpolar. The second one, ammonia. Nitrogen is way more electronegative than hydrogen. So nitrogen is winning, nitrogen is winning, nitrogen is winning. As a result, the whole molecule is going to move upwards. That's a polar molecule. Water, angular geometry. Oxygen is winning. Oxygen is winning. How do you know that? Because oxygen is way more electronegative than hydrogen. As a result, the molecule is going to move upwards. So nonpolar, polar, polar. All right, practice predict the polarity of, so many molecules. CH4, CH3Cl, CH2Cl2, well, all right. Remember the 3 steps: molecular geometry, bond polarity, then finally molecular polarity. I have all the loose structures written out for you. Again, I focused on the center atom. I ignored the lone pairs on the outside atoms. Not a big deal in this case. All right, these are the loose structures. Okay, let's use this one as an example to say you cannot use Lewis structures only. You must use the molecular geometry. For example, if you are looking at this molecule, from the Lewis structure, you're going to say, okay, all the forces cancel each other. Chlorine is more electronegative. Chlorine is more electronegative. However, they cancel each other. Well, from the Lewis structure, they do cancel each other. However, if you look at the molecular geometry, the true shapes of the molecule, I also put them here. Again, the center is a carbon here for all of them. Now you're going to see, oh, wait a minute. If they are playing the tug of war, chlorine is going to win, chlorine is going to win, carbon is going to win, carbon is going to win. This whole molecule is going to move towards that direction. Does that make sense to you? The two chlorine, the forces from two chlorine pulling away from carbon, the two forces do not cancel each other. They are angled. They are not opposite to each other. So you must use the molecular geometry before you consider bound polarity. You can go through this by yourself with the molecular geometry here. You can pause the video, try to predict that, and you move on. I will give you the answer. All right, this is going to be nonpolar. This is going to be polar. This is going to be polar. We did this one already. This is going to be polar. This is nonpolar. So what do you see here? We started from methane. Each time we are replacing one hydrogen with a chlorine. So one hydrogen is replaced, two hydrogens replaced, three hydrogens replaced, all four hydrogens are replaced. Talking about polarity, the molecule goes from nonpolar, polar, 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 finally nonpolar again because all four hydrogens become chlorines. They will cancel each other. True or false? A molecule that has polar bond will always be polar. No, we concluded this at the beginning of this lecture. Polar bonds are not enough. You must consider the molecular geometry. If false, provide a counterexample. A counterexample would be carbon dioxide. Carbon dioxide has polar bonds in it, but because the molecule is linear, the two forces, the bond polarity cancel each other. That's a nonpolar molecule. So that statement is false. Another practice, figure out the polarity of 1, 2, 3, 4, 6 molecules. You can pause the video, go through the procedures we learned earlier, and make your conclusion on each of these molecules. Then continue the video to see the answer keys. These are the polar molecules. The first one, the last one, nonpolar. All the others are polar molecules. Did you get them right? See you next time.